you. I'm Sara Miller. I'm working with Professor Brittany Schmidt at Cornell University, and I am working to build a global circulation model for the ocean at Europa. So before we move on, I wanted to kind of point out the cover image I chose, which is primarily because I thought the colors made for a pretty PowerPoint theme, and secondarily because it shows some interesting kind of structures that exist on the ice crust on Europa. So as you can see, it's not a smooth ice skating rink. It's a very interesting and geologically active zone, which hints that probably the interior is a dynamic and very interesting place to study, which is what I'm going to talk about next. Before I dive into the science, I do want to take a moment to thank my team and kind of the people who have helped me bring my understanding in this field up. So I have a background in fluid dynamics and aerospace engineering, which I'll talk a little bit about throughout this talk. But these people have been really instrumental in kind of working with me on the planetary aspect, as well as my funding sources through an NSF GRFP and a NASA Finest and an Amelia Earhart Fellowship, and some wonderful people who support this work. Okay, so as I mentioned, Europa has a very interesting surface, and it hints that there is a dynamic ocean interior. And I think that the ocean circulation, the physical oceanography piece of this puzzle, is a really interesting one in terms of habitability, because when we look at Earth's ocean, the transport of heat and salt and nutrients throughout the ocean column is really what sustains our biosphere. So I think it has really interesting habitability implications on other planets as well. And specifically, I want to narrow this down even further. The region of our ocean that separates the glacially covered parts of our ocean from the liquid layer, that ice-ocean boundary layer, is really instrumental in setting far-field ocean properties. So that tiny boundary layer region between the ice and the ocean actually has an outsized effect on affecting global water mass transport. And so I think that's very much worthy of intense study in the modeling realm for Europa. So I'm not the first person to attempt to build a global circulation model for Europa, but the state of the field is really kind of divergent. So models of Europa generally fall into one of two categories, depending on kind of how you set your boundary conditions and really how you set up this ice-ocean interface mathematically. So usually there's kind of an outsized effect of either the rotation-driven or buoyancy-driven, so kind of temperature salinity gradients in the model, and the results are very different. So global circulation models exist. They usually fall into one of these two categories, and they do not agree with each other. Now, if we look at terrestrial ocean models, on the other hand, they look very different, and that's because they've had a lot more scientific manpower and years of study and actual data, so how nice for them. So their models are very sophisticated compared to what we see in planetary ocean models. That being said, there are still kind of parts of Earth's ocean that we don't understand. So it's very much, ocean modeling is an active area of research, and there are still some mechanisms that remain poorly constrained, which is really humbling to think about doing this on a body that we have zero data for, and know a lot less about. But I'm going to try anyway. So let me introduce you to the tool that I'm using. So I'm using the MIT General Circulation Model. So it's a 3D circulation model that employs the full non-hydrostatic incompressible Navier-Stokes equations. It also has some really interesting and very useful packages for Europa. So an ice shelf package, a deep convection package, which is really helpful because Europa, unlike Earth, has a really deep ocean compared to its planetary radius. And that is important when you're talking about large-scale flow features. So I won't kind of dive into the nitty-gritty. It's written in Fortran. So if you're a modeler, you probably just cringed. But yeah, it's a very powerful, very useful tool. So there's lots of knobs that you can turn within this model, and I'm working on turning kind of all of these through sensitivity studies throughout my PhD. But what I want to focus on in this talk is the role of topography underneath the ice shelf. So in this case, I'm talking about both the small-scale topography, so surface roughness of the ice, which affects things like turbulence in the boundary layer, as well as large-scale features on the ice that can form large-scale flow features. Now, you might be thinking, like, why would a turbulent boundary layer affect global ocean circulation, and specifically habitability for this interest? And I want you to remember that the ocean timescales operate a lot faster than planetary timescales, and that could be an important link for a habitability argument. So a quick review of kind of boundary layer physics. I took out the full equations because they're pretty ugly, and I just have these like nice kind of simplified relationships that I want to discuss. So I'm using kind of a widely adopted parameterization called the 3-equation parameterization. It's very creatively named. And essentially it's just looking at the fluxes, those are those Q values, between a solid ice shelf, which is freshwater or fresh ice, a mixed boundary layer region, and then the mixed layer, the liquid ocean. So we're looking at kind of the 3 unknowns in these equations are the temperature and salinity of the boundary layer, as well as a melt rate, or m dot, which is negative if it's melting, positive if it's freezing. And that's kind of how we're constraining the phase change that's happening at this region. So I'm using a model that's kind of an ongoing international effort within the MIT GCM community to model this kind of physics for Earth's ocean. And so this is a simplified version of that math. So it's a 2-equation parameterization that's assuming the salinity of the boundary layer and the mixed layer is the same. Current research and kind of more recent results since submitting this abstract, I've been able to like use the 3-equation parameterization, but those graphs are still pretty ugly. So maybe next AbGradCon. Yeah, and kind of one other thing that's very common on Earth, but not a great approximation for Europa, is that often in ocean models, the pressure dependence of density is approximated by depth dependence. I mentioned that Europa's ocean is a lot deeper than Earth's. So this is something that I've removed as well, because I think no longer holds for Europa's ocean. So I mentioned it's probably not like a flat ice skating rink under Europa's ice shell. We don't know what it looks like, but it's probably not that beautiful and simple. It's probably not this beautiful and simple either, but to start with, to kind of demonstrate some of the flow features that might develop with ice shelf topography, here's like a very simple ramp that I'm introducing. So it's not a global model quite yet. It's just a rectangular domain starting at a fixed initial temperature. And we're going to introduce a heat gradient and a flow through ice melting and see what develops. So we're seeing some already, just with very simple geometry, interesting and kind of recognizable flow features. So we see the development of what looks kind of like a western boundary current on the left and an ocean gyre on the right. And these are happening because there is melting happening at depth. So if you remember the phase diagram of water, there is a pressure dependence on the melting point of ice. And so we see melting happening on the bottom of this ramp. And then as the fresh water is rising along the meltwater, the ramp, it's circulating, and that's creating a circular flow feature, this gyre. So we have on the left, these are just stream functions, the barotropic stream function, and then the right, an overturning stream function, just in a couple different directions. So maybe more importantly, the melt rate, what's happening. So we're seeing both regions of melting and freezing. The contours got a little dense for the melting, so I just kind of outlined that where that's happening there. But that's happening kind of as the warmer ocean mixed layer water is interacting with this frozen ramp. And so we see that kind of already just very simple geometry, there's lots of dynamics happening. There's freezing, there's melting, there's flow features. But this is probably not very realistic. Maybe more realistic is something like this. So this is a almost global topography that I stole from what Earth's ice shelves look like. I cut out the poles because of convergence issues. And it's a pretty coarse resolution, but it still captures a lot of the large-scale flow features that we see on Earth, as well as some turbulence and mixing effects from small-scale features that are missing. And so I think it's really important to think that like when you're modeling heat transfer, like your grid resolution is really important. So the size of your grid cell in your model affects kind of how quickly heat is transferred through your ocean. And so this is really too coarse to understand what's happening in turbulence and boundary layer effects. So I'm kind of accommodating that in the model by modifying the MIT GCM to have like spatial grid remeshing. So I'm slicing up the grid cells so that I can have melting and freezing happening within a single model run, which is not kind of the standard configuration, within the boundary layer. So this has been kind of very helpful in understanding turbulence and more quick timescale melting and freezing physics. Now, this is kind of one of several things that needs to happen to have a more realistic ice shell, is like greater spatial grid density in the boundary layer. There's also, but even so, it's not going to be a simple ramp. There's other things to introduce, like different heat and salt transfer coefficients, a mushy layer. There's interesting work that's being done by Jacob Buffo, if you want to look at his work. So in my model currently, the ice is assumed as a completely freshwater layer. That's probably not the case. There might be zones of brines and interesting kind of pockets of heterogeneities that will affect these processes, but this is kind of all just taking steps to introduce more realistic features into an ice shell model, and then look at the global circulation effects of those features. So to wrap up this little bit that I've discussed, terrestrial models I think can be very valuable in the planetary community. Within those models specifically, I think there still needs to be a lot of work done on the ice-ocean boundary layer, which is what I've been focusing on this past year of my PhD, and the potential impacts for habitability of this kind of great resolution on an ice-ocean boundary layer could be very important for habitability. All right, and I'm happy to take questions.
So if you are assuming, so with the mushy layer, like a slurry, for instance, is the assumption of incompressible fluid still valid? And does that change? That makes Navier-Stokes much more complicated, right? So how would that really affect your modeling? Would you have to change some things, or?
Yeah, no, that's a really good question. So realistically, yes, you would change the kind of forcing equations. So the model as it currently runs, it assumes that, it's kind of backing up a little bit, the equation of state of seawater is a linear function of salinity. So if you introduce something like a brine, it's removing that kind of linear assumption. That said, the model as it currently stands, it does have a solid ice layer, so it doesn't look at brine pockets or mushy layers yet. If you wanted to do that, I do think that, yeah, you'd need to change the equation of state of seawater locally, to accommodate those.
And what about the incompressibility assumption?
I think that's a small enough one where if you're looking at the effects on overturning and flow, it wouldn't have an effect, but it would be a very cool sensitivity study. So that's a good question. Thank you.
Thank you.
Hey, sorry, really ignorant question. So with Europa, it seems like there's a very kind of noticeable temperature gradient. Is that just due to pressure, what's at the middle of Europa?
Ooh, interesting question. Okay, I think I have a backup slide that might help. So yeah, so the mechanisms that are kind of important for Europa heating and what's sustaining the ocean are tidal heating, that it bottom heating from residual heat of formation, internal heat. If there is this dynamic ice shell that's freezing and melting, like I think it is, then you have heat fluxes from freezing and melting. So there's a lot going on. The kind of weights of these effects is still very much unknown, and so that's why I'm really trying to use observations from Earth. So for instance, I'm using turbulent transfer coefficients of freezing and melting from Antarctic field studies to kind of influence this model. But yeah, it's really there's a lot going on, so it's really kind of the challenge is trying to figure out which one is driving the thermal gradient.
Thanks.
Okay, we have time for one more question.
Taylor Plattner at Georgia Tech. Great talk, Sarah. You were talking about brine pockets to make the model more realistic. Do you plan on doing that with your model? And have they done it on Earth, with Earth models? Have they even thought of incorporating brine pockets?
Yeah, it's a good question. So the answer is like no. Most like glacial models and global ocean circulation models don't include brine pockets because on Earth those are more seen in like lake environments or kind of like the like hypersaline lakes and flash frozen lakes that like Jacob works on. They might, Europa's different conditions though. And so they could exist there. So at most, I think I would do a case study on what would happen if brine pockets exist. So it's something I'm working on now. But it's not something I'd include in every run because it's just still very much an unknown.
Yeah, I was going to say that was kind of like a loaded question, but I was just curious.
No, it's a good question. Yeah.
Okay, thank you so much for the talk.
Thank you.
Thank you.